Let's look at an example of two-dimensional projectile motion using vectored value functions. Let's start with this really simple but incredibly profound idea that I absolutely just love. Got to start with this. When we're studying an object falling, say this is a projectile, it's in free fall, there are no other forces on this object besides gravity. I'm going to not include air resistance and just study the influence of gravity on the motion of a projectile. So let's begin by looking at that force, and that force of weight of that, what makes that object fall, its weight, is described by this m times g. This product is mass times acceleration, where this g is the acceleration that causes the motion that causes the object to fall. Now, if the force that is giving the object weight, that is making it fall, is only due to gravity, this is an expression that represents the force of gravity between two objects that this projectile would feel from the mass of the Earth. So this big G is some gravitational constant that just depends on whatever units we might choose for the measuring the mass of the Earth and the mass of our projectile, and whatever distance we might be from the center of the Earth. That would describe the actual force of gravity on the object that is this projectile. So if it is the force of gravity that is causing this motion, of course the force of gravity is what gives it its weight, and if it is the weight only that is causing the object to fall, what we can do is we can solve for the acceleration of that object. And the amazing thing is that it doesn't matter what the projectile weight actually, or doesn't matter what its weight is, it doesn't matter what its mass is. The simple, profound thing that I was trying to get to is the fact that I can cancel these m's on each side of this equation here and say that the acceleration of this projectile is the gravitational constant g times the mass of the Earth divided by the distance from the center of the Earth, or from the center of the mass of the Earth. That is the constant acceleration due to gravity. If you are near the surface of the Earth, then this d is minuscule change compared to the total distance. And so while in fact this acceleration isn't really constant, it depends on your distance from the center of the Earth. What we often do in examples like this is that we say, if you are near the surface of the Earth, the distance isn't changing very much, and so this is nearly constant. We've got a constant mass of the Earth, we've got a very negligible change in the distance from the center of the Earth, and so it's this big G, mass of the Earth, distance from the center of the Earth, that is just nearly constant. This is where we get these numbers that you often see, these kinds of questions, where if we're measuring in metric, we'll have 9.8 meters per second squared as this acceleration due to gravity, or we might use 32 feet per second squared as this constant acceleration near the surface of the Earth due to gravity. I'm not putting negatives in these right now. The negative is something I might use depending on if I want to include direction in the model when I use this constant. All right, and that's exactly what I'm going to do as I move on here. I'm going to put this into a vector-valued function that describes motion without air resistance for projectiles. So let me begin by sort of tracing out a picture here of what we have as our beginning elements. Let's imagine a vector-valued function for the acceleration of our projectile. Let's write that as negative g times the unit vector j. What that does is just takes this constant acceleration g, that could be 9.8 or 32, and then it gives it a direction down in the xy plane. The negative and the j vector form the direction for me right here. So this is the x-axis. Then I have negative g times the unit vector j is this acceleration vector. Now notice that it doesn't have any factor of t in here. This acceleration does not change over time. It is a constant acceleration due to gravity. Another piece of one of my beginning elements is a a vector v for the velocity, and I have, let's say, given an initial velocity that I'm going to leave it completely arbitrary. I'm going to use this to derive some formulas that then we can use as to do an example at the end. So v0 is the initial speed, really. It's the magnitude of the velocity at time 0. And this angle theta is this initial angle of the velocity relative to the horizontal. So you could see theta right here as this initial angle relative to the x-axis for the vector v. And then this another element that we have as a given parameter at the beginning is an initial position for our projectile. And I'm going to write that r as this position vector. But let's say we only know the value at time 0 is some initial height. So we'll just call that h sub 0 as my initial height. So this would be h0 is this value that's a y value in the xy plane that represents this initial height. Now, when the object is launched with this initial velocity, it moves off in that direction, but then it's brought down by gravity, and we'll have a vector r that changes over time that traces out the position of the position of the projectile over time. Maybe this is a good place for me to say how this acceleration vector, being a vector, it can be drawn anywhere, and it is always acting on the projectile, and it's a constant vector. It's a constant vector that always influences the motion of this projectile back toward the ground. All right, so now moving along from that, let's derive a formula for the velocity of a projectile, knowing only the fact that it has a constant acceleration due to gravity. So if we're going to find the velocity, we could say, well, this is going to be an antiderivative to the acceleration. So we can integrate with respect to time this acceleration vector and write it this way. And while there are several different ways that I could go about writing this, I think I'm going to do it this way. I'm going to go negative g, unit vector j, integrated with respect to time, and then do this writing in the following way. I'm working in a two-dimensional space here, and so when I integrate this, I want to recognize that there is a potential component in with the unit vector I, and actually right now in the derivative that component is 0, but in the antiderivative it's going to be some constant. So let's write C1 unit vector I to represent the constant that is the antiderivative of the 0 in the acceleration, plus, and then integrating with respect to time, where I take g to be a constant that doesn't change over time, I'll get negative gt, and then plus some other constant that I'll just call c2 right now, and then all of this I'm going to put on the j component. So this is my antiderivative, and to sort of confirm that this is what I intend it to be, I would think about now taking a derivative of this line here. Say, you take a derivative with respect to t, and this is some constant that doesn't change over time, its derivative would be 0, and there would be no I component in the acceleration. And taking a derivative of this component here with respect to t, then I would just get the negative g, and then plus 0 as I take a derivative of this other constant. So I get just negative g in the j component in the derivative that is this integrand here that is my acceleration. So this represents the velocity at any time. So let's write that again here. This is the velocity function at any time. And I did know the velocity at time 0 as a given parameter here. So let's put this information together. If we were given initial velocity, and I want to write it maybe like this. Velocity at time 0 as a vector is some scalar v0 that is the speed or magnitude of the velocity, cosine theta, where theta is a constant. Very important to recognize that theta is a constant. That's the initial angle of the velocity. Of course, the angle of the tangent as it moves along changes, but this is only the initial angle, and that doesn't change. The initial angle is always the initial angle, so theta doesn't change. I plus sine theta j. This is my initial velocity. Yep. So let's say if this is always the velocity at any time, then it would have to be the velocity at time 0. So let's use the fact that if you plug in 0, you should get this, right? So we'll say v of 0 would be c1 I component plus, say, negative g 0, that's time 0, plus c2, all j component, but that's also v0 cos theta I component, and here I'm just distributing, of course. So if I have these vectors equal, then their components are equal. What I'm trying to say is that c1 must be v naught cos theta, and then this must be v naught sine theta, and this is all 0. So we're getting that the constant c1 had to be v naught cos theta, and c2 has to be this v naught sine theta. So a conclusion that we can draw from this is an expression for the velocity at any time has to be v naught cos theta. V naught is the initial speed, and theta was the initial angle, plus, now I'm drawing on the fact that I have found what the c2 would have to be, and so I'm going back to what the velocity vector would be at any time, and using that, I have negative gt plus what the c2 value would have to be, v naught sine theta, and this is the j component of my velocity vector. This is a valuable conclusion right here. Put a circle around that and don't forget it. Useful information. We know the velocity at any time. This would be for some projectile in free fall that has some initial velocity, but there's no air resistance. Okay, certainly you know what the next step would be. We're going to figure out the position, not strictly only the height, but the actual position vector over time. So I've derived this function for the velocity at any time, and maybe just also, before we go a little further, notice this is all constant horizontal component. Of course, the vertical component of the velocity is not constant. It may be, depending on the initial speed, going up, having a vertical component. The vertical component of the velocity might go to 0, so suddenly the vector could just be a horizontal line, and then as the vertical component of this vector could turn negative, then this vector starts to point downward, as a typical path would look like. So as we see this projectile, we might have a place where the velocity has 0 vertical component, then later it has negative vertical component. That's another thing that I could say about this, is that r is the position vector, and the tangent, the velocity, is always a tangent vector. So at different times we'll have different position vectors with this tangent vector. It's natural to draw the position vector always from the origin to locate the position of the projectile as the terminal point of your position vector, and then it's natural to draw the velocity as a tangent. You could draw the velocity vector anywhere, it's a vector, but it's natural to draw it as the tangent to the path, a tangent to the trajectory. And then you could think of the acceleration as always this vector that is acting upon the projectile, something like this. And so this is the idea. Now we're going to derive the position vector r. So it's the position of the position of the projectile as a vector at any time. Well, it's an antiderivative of the velocity, integrating the velocity over time. And just another way to see it, just to maybe the derivative of the position vector is the velocity, right? So if I want to find the position vector, I have to integrate the velocity. So if we integrate this velocity vector, we have two components. This is a constant in the I component, and we have this variable j component. Significantly important. First of all, integrating with respect to t. v0 cos theta times t plus an arbitrary constant that comes from the integration in the I component. So we can call this any letter, and I think I'll just go ahead and say C3, a third arbitrary constant that comes up in this integration. And all this has to be on the I component. Now, take a derivative with respect to t, and you have to be back here just on the I component. Let's now move on, take a derivative with respect to t on the j component. We'll get negative g, and then t squared over 2, that's antiderivative of t, where g is just a constant, plus v0 sine theta, and technically this is all constant, times t, and then some arbitrary constant. I'm going to have to go to constant number 4 on the j component. Now, remember we had some given initial parameters. Let's say we know the initial position at time 0 is just some height. That's the position vector, initial position vector. So I know that in particular, if this is my r, t, position vector at any time, it should agree with my initial condition that at time 0 we have this position vector. So let's plug in 0 into this whole thing and resolve what these constants have to be. So r of 0 would have to be b0 cos theta times 0 plus constant number 3 in the I component plus, now this would be negative 1/2 g 0 squared plus v0 sine theta times 0 plus c4. All of this belongs in the j component. So this means we've got c3i plus, now that's 0, and because this is 0, all of this equates to 0, and we just get this constant number 4 on the j component. And let's go back and say, well, if you have a position at time 0 that is just h0 in the j component, let's say it's also expressed as 0 on the I component and h0 on the j component. And so here it is. Hope maybe you can see where this is headed. At time 0, this is what the position vector has to be, and this is what it is for my integration, and that means c3 would have to be 0, and c4 would have to be h0 to agree with this initial condition. We're able to solve because these two vectors, of course, are equal. R at time 0 is got to be r at time 0. So to be consistent with everything that we've developed so far, then we make the logical conclusion that c3, that constant's got to be 0, and constant 4, that's got to be h0. And so I have it now done. Position vector at any time is, in the I component, v0 cos theta times t. Here's where I'm dropping those extra parentheses because it's just simpler to write and understood, hopefully, in the context. Plus 0, right? So that is my I component for the position vector. And the j component, negative 1/2 g t squared plus v0 sine theta t. Now, it's a little bit off the screen here, but if we go back, it's right here. This is where I'm getting it. I just found that c4 had to be h0. I'm just copying all this. Okay, that's it. That gets another circle or a box. It's a major conclusion for your projectile motion. This is my position vector. That's really what I was setting about to derive, a function that can describe the position in two-dimensional space of a projectile that's acted upon only by its weight, and that doesn't include air resistance, which can be negligible if you are talking about maybe a bowling ball or a cannonball that's being shot for a relatively not too huge of a speed and not too huge of an altitude or distance. If this can be a good approximation for the position of something, a baseball maybe that you throw, not too far off if we don't include air resistance. At least it's a good start for understanding motion when you include air resistance. All right, so here I've collected everything together. A is a vector, a constant acceleration due to gravity that we could just say is minus g, where g is this acceleration due to gravity that's constant near the surface of the Earth, either 9.8 or 32, depending on the units. We can then say the velocity vector is given by this v naught cos theta on the I component, negative gt plus v naught sine theta in the j component. R is the position vector. It's v naught cos theta times t, I component, and negative 1/2 g times t squared plus v naught sine theta t plus h0 in the j component. V naught is the initial speed, theta is the initial angle of the velocity vector relative to the horizontal, and h0 is the initial height. One last little comment is that you may be familiar with this component measuring just the height, just the y component of it's parabolic without air resistance, and this describes the position in the y component of the y component of the position vector, and this describes the horizontal position, horizontal component of the position vector. It's really fascinating how these guys are independent components, but work together to describe the position in two-dimensional space. Let's do an example with a given initial velocity and initial height, and determine the position of the vector, position of the projectile, and how far it goes and how far it travels through its path. We'll do an example using these vector valued functions. Let's do an example now where we are given an initial height of 5 feet, initial speed of 50 miles an hour, initial launch angle at 30 degrees, and let's find the range, the height, that is the maximum height, and then the length of the trajectory, that is the actual arc length of the path that it follows. Well, let's begin with our position vector and fill in all of our parameters. Position vector looks like that, but we got to make sure our units are good. So the fact that I've got this initial height in feet and I can convert miles into feet, I think I'll do everything in feet and proceed that way. So if my initial velocity is 50 miles every 1 hour, then let's convert that into feet per second. I know 5280 feet's 1 mile, and 1 hour is 3,600 seconds. So we're looking at about 73, let's round it off. Initial velocity about 73.3 feet per second. Yeah, from that we can just go right into the position vector. This is cosine of 30. Yeah, so there's my initial velocity. Cosine of the initial angle times t in the I component, negative 1/2. There's the g value that I'm choosing because I'm doing things in feet and seconds here. So acceleration of 32 feet per second squared. 73.3 for the initial speed, the sine of the initial angle times t plus that initial height 5. So this will work out to be think, it's reasonable to do some approximations here, even though we could get the exact value for the cosine of 30. Because we have to deal with this speed, I think going into a decimal here is fine. So this is the position vector that I can use now to trace out the path. To answer the questions, we want to know the range, we want to know the max height, and we want to know length of the trajectory. So let's work on the range. So the range would come from the horizontal position when it hits the ground. So what we need to do is figure out when the y component goes to 0. So we'll solve this y component when it's set equal to 0. That's just going to take a quadratic formula. Well, obviously the negative time isn't going to apply in this case. It would be where the time, if it followed the same trajectory when it would have been on the ground before it reached that 5-foot initial height. So we're going to discard that, take this as the time when it hits the ground forward in time. And so if we know the time when it hits the ground, then the thing to do would be to use that time in the horizontal component. So the range is just using the horizontal component of the position, right? So the position function, this is the x component, this is the y component, and it's now, we know the time when the y component is 0, so let's figure out what the horizontal component is at that particular time. So we're going to do 63.5 times the time. And, this is approximation. You might be slightly different in your answer because we could round off each of these values slightly different. Or say about 151 feet range. Okay, so let's move on to the question of finding the max height. And this will happen when the y component of the velocity is 0. We had to find when the y component of the position was 0 to know when it hits the ground. And now to find the max height, that occurs when the y component of velocity is 0, when it's reached its apex where it has a 0 vertical component of velocity. You notice, by the way, that the velocity is never 0. It always has a horizontal component of velocity. It continues moving horizontally, but there's an instant when it reaches its vertex maximum height when the horizontal component, when the vertical component of velocity is 0, when the y component of the velocity is 0. So my velocity vector was, we actually haven't, I haven't really written that exactly yet. So in general, this would be the velocity in general. Now, also I could have actually gone back to my position vector and just done a derivative. In fact, that'll be easier for me to do so I don't have to recompute these values. So just getting the velocity from the position vector, this will be 63.5 on the I component. And this will be negative 32t plus that 36.5 that I had calculated here. That's just a constant term in the velocity. So that is the velocity vector, and my objective here is to find the time when this y component is 0. So let's do that. That is not necessarily going to be halfway to the time when it hits the ground, because this projectile did not leave from the ground. So the time when it reaches its highest point is at 1.14 seconds. And so what we want to know now is what is that maximum height. So I have to go back to the position vector at time at this instant. But I only need the y component. So let's just get right to the answer. So we'll just say y component of position So there's the max height for this projectile. Let's move on now to one last calculation. Let's get the length of trajectory. If we call that some distance, what will happen is, in order to find the distance that it travels, I'm going to find the I'm going to integrate the speed over the interval of its path, over the interval of the time it's in flight. So this is a really fundamental, important principle of calculus in general. Is this sort of net change theorem is the way that's often named. By adding up the speed at every instant, this instantaneously changing speed, by adding up the speed at every instant, I am really multiplying rate times time instantaneously for the entire interval of its trajectory, and in that way finding the total length that it actually travels by adding the speed at every instant. You could say that what we're doing here is calculus, and before calculus you just have this principle where you might have a constant rate or average rate. What I can handle now is this magnitude of the velocity equal to some rate that's instantaneously changing. So this is the speed. And if the speed is changing continually during the trajectory, we can find the length of the trajectory by integrating that speed over the interval that it's in flight. So this is the way we'll do it. And it's from this velocity vector we can compute the speed. And you can see this is a speed that changes over time. And if we want to find the length of the trajectory, what we'll do is we'll say that that distance is from the initial time 0 to the time when it hits the ground. And we figured out that it hit the ground previously. Remember computing previously that it hits the ground at 2.38 seconds. Now, we could find an antiderivative for this function by a trig substitution, but being a word problem and a practical problem, it really makes sense to get a decimal approximation anyway. So I'd like to do this one using the calculator and just type into the calculator this rate function and integrate over that interval. And also we talk about what that graph looks like and the significance of it. So let's do that. Okay, so now I've got my TI-84 here, so I can type in this. This function, remember, is speed. This is the speed magnitude of the velocity. And that's what I'm going to type into the Y editor and try to visualize that graph of speed over time. That negative is important there. There's no need to simplify it when typing it into the calculator. It'll work just exactly perfectly like that. Now, maybe think a little bit about the window before you just go right to the graph. What do we expect? Remember, the initial speed was 73 feet per second, roughly. And as it goes up, it should slow down and then speed up again. So I really think 73 is pretty near to the maximum, it actually may end up going a little faster as it goes those last 5 feet down when it passes its initial height. So let's set a window that captures that. And we also know that the whole thing hits the ground in well, we have it here, about less than 3 seconds. So set a window that captures that. How about we go from time 0 to maybe 5 seconds. Count by 1 second. And then a minimum y value. These y values are the speeds, and let's put this at, how about 100? Take a look at that. So that's the speed over the first few seconds. You notice the speed comes down and then it goes up again, and it hits the ground, and so probably it no longer really is valid after 2.38 seconds. This model would only go up to that point when it hits the ground. So let's figure out the area under this curve that represents the speed, and that area is actually the distance in feet, because you're multiplying feet per second times seconds. You're getting total accumulation of feet traveled, and so let's get that. So to get the area under a curve, we can go to second calc. Once we have the function in second calc, and then pick number 7, that option here. And the lower limit I want to take is 0. And the upper limit I want to take is 2.38, roughly. And it's finding the area under the curve up to that point. I get about 159.8, let's say. 159.8, okay. So that sounds pretty good. That is the distance that it travels if you actually look at the arc of its trajectory. We had found that the range was like 151, so this makes sense that it's just a little bit more. Maybe it's because it was only 30 degrees in that initial launch angle that this isn't that much more than the range, because it doesn't travel that much high, up that much high before coming down. Okay, so that's it. That is the end of what I wanted to do with this video. I hope it was helpful and useful.